Hi, welcome back to another lecture in process control automation. This is Nagarjuna, and today's topic is ladder logic programming. So basically in PLC we have different languages, different programming languages, but most widely used is ladder logic programming. So I'll just give you what are the different programming languages available for PLC. So for a PLC, one can have, there are two types. Okay, so one is categorized into text based, and the other one is classified into graphical user interface. So here are the textual languages, and here we have a graphical a language, or GUI based. Right, so here in the textual based, we have an instruction list, and also the statement list. Whereas in graphical user interface, or GUI based, we have a ladder logic. Next we have FBD, functional block diagram. And then we have a statement, SFC, sequential flowchart. So these are all the various languages for PLC programming, but one most widely used, and even I like most, is the ladder logic programming, because it is very easy to write and easy to understand and very simple in creating logics. So now let's look into this language, right? So now coming to the ladder logic, here in the ladder logic, one must understand the basic, we use very simple instructions here. So the first instruction here is normally open. Normally open. In some books they refer it as examine open. Next we have normally closed. Or examine closed, and then the output. Okay, so as I mentioned already, that ladder logic will make you, it is a GUI based. So here we don't write any text based instructions. We use only the symbols. So here there are three instructions on the screen. One is the normally open instruction, one is the normally closed instruction, and the output instruction. So based upon these three instructions, one can write very beautiful programs, and they can able to construct switching applications, and later on we can also develop the sequential applications by using these three instructions. So these three instructions are very, very powerful instructions, I can say. So we need to understand its operation very carefully. So now let's look into the normally open instruction and its operation. So and one more thing, this notation, these names, normally open, normally closed, and output, these names look very familiar, right? Yes, that's true. These names are derived from the relay logic. You know that the PLC, before the PLC, we used to work with the relay circuit boards. So earlier we used to have this relay boards, and later on, after after coming these programming devices, so we started using the PLCs. So computation, when the computation started, so so we brought this programming concepts into the controller, and then we started using PLC designs. And here we use the same notations, normally open, normally closed. So now let's look into this normally open instruction. So basically by name it says normally it is open. So Now, for this instruction, the input to this instruction matters a lot. So what is an input? See, all these three instructions are bit level instructions. So the input, say for example, the input to this instruction, if it is 0, if it is low, now what happens? The state of this instruction will be unchanged. So what is its state? It's open, so it's unchanged, so it remains in open only. So which means there is no contact, it means there is no output at all. So when I connect this NO followed by an output, so here what happens? As long as if the input is 0 for this instruction, the output also will remain open, so the output remains open. Clear? Now suppose if I give an input to this instruction, now what happens? The property of this instruction will change. So it becomes normally closed. So it changes its property from normally open to normally closed. So when this instruction becomes closed, then you will get an output as high, because previously the contact is open, now the contact is closed. So when the contact is closed, you will get a continuity over here and the output goes high, or the output gets energized, isn't it? So that is a property of this instruction, normally open. On the other hand, we have a normally closed, so followed by an output. Here the instruction property by default it is closed, so the contact is by default closed. So when there is no input, it what we discussed in the previous, unchanged, the property is unchanged. Same applicable over here also. If the input is 0, the instruction property is unchanged. So what is the property? Closed, so it remains in closed. So it means the continuity will be going on and you'll get output as high, right? And now when I give input to this instruction, now what happens? The property will change. So closed instruction becomes open, and we get output as 0 because there is no contact, and becomes open, no output. So the operation of the normally open and the operation of normally closed instruction are quite opposite, right? So once again, this understanding of this property is very, very important for one to build a logic, because in the next step we will be doing some switching applications. So for all switching applications we will make use of this NO, NC and output instructions only. So this operation, this understanding is very, very important for a ladder logic development, right? Now let's we will see one simple exercises. We'll do some logic gates, right? So we'll do some logic gates, and before that we need to understand a simple concept called Boolean expression to ladder logic. So you know that all digital electronic designs are based on the Boolean expression. So if you have a Boolean expression with you, you can able to design any kind of a logic, isn't it? So most of the combinational logics are based on the Boolean expressions only. Let's take a few. As I said, logic gates. And so the operation, for a 2 input AND gate, the Boolean expression is A dot B, right? A dot B, the AND operation between these two literals. Similarly, if I take OR, it is A plus B. It means the OR operation between the two literals. Similarly, if I take a NOT, it is a complement, a literal with a complement. And I can say NAND, it is a dot B whole complement. It's a complement to the AND operation, and this I can write as A bar plus, because dot and its complement is plus, B bar, right? So similarly, NOR A plus B whole bar, and this I can write as A bar dot B bar, right? Same is the case with the XOR. I can write this as A XOR B, if I expand this, A B bar plus A bar B. Now, when you look at this logic gates, in every gate there is a Boolean expression. So this is a operation, and this is a Boolean expression, right? Now, if you know how to convert any given Boolean expression into the ladder logic, then any kind of a combinational design, you can realize that easily into the ladder logic. So for that, you need to understand very simple things. That is, whenever you see a normally a literal, so I'm giving the rules, or just a thumb rules, you can say, conversion rules means ladder logic, Boolean expression to ladder logic conversion rules. So whenever you see a normal literal, you replace it with normally open instruction, whether it is a single literal or a double two literals, right? So each literal has to be replaced with and its equivalent instruction. So if you see A, then replace it with normally open, right? If you see two literals, then two instructions you need to place. Remember that. Similarly, if you see a literal with a complement, then replace that with normally closed instruction. When you see a normal literal, normally open instruction. When you see a complemented literal, then replace it with normally closed. Then if you find a dot operation between the two literals, then the combination should be series. Remember, when you find a dot operation between two literals, the combination should be series. Similarly, when you see a plus operation between the two literals, then the combination should be parallel. Just if you remember these four things, then you can realize any ladder logic, any given Boolean expression, you can realize into the ladder logic. So let's take an example, that is A dot B and operation. So in A dot B and operation and ladder logic. So I'll take a new page and ladder logic. So we know that the Boolean expression is A dot B, right? Now, when you realize this with the ladder diagram, as I mentioned, you find a literal with a without a complement A. So I'll put one normally open, then dot operation means series. So another literal, that is B, without any complement. So again, normally open instruction, then followed by the output. That's it. So this is my A, and this is my B, and this is my output, let's say Q. Now let's verify with the truth table, right? So the truth table says A, B, Q. So 0, 0, right? So 0, 0. So A is 0, B is 0 means unchanged. So the instruction property of A will never change. It remains in open. Similarly, the B also remains in open. So both the instructions are in open, which means there is no continuity to this output. So the output also remains 0. Clear? Next, 1, 0. Now this A has received the input 1. So the property of this A instruction will change to normally closed, whereas the B remains open, unchanged. So one of the contact is closed, another contact is open, and both are in series. So still there is no continuity to the output. So still the output remains 0, right? Next, 0, 1. Now this time B gets changed, B becomes closed, whereas A unchanged remains open. Still there is no continuity, so output is 0. Now finally, when A and B both are high, it means both instructions will change its property. Both instructions will change from normally open to normally closed. So the continuity will appear across the output. So we get the output as high. So with this, now we can say that this logic is working perfectly for AND operation. So if both the contacts, both the instructions, if they are true, then we are getting the output as high. Clear? In the same way, you can verify any given logic. So let's take XOR. XOR, right? So what is the XOR table? XOR truth table says here 0 0 0 0 1 1 1 0 1 and 1 1 0. So XOR says that if there are if the two inputs are same, then the output is 0, right? And if the inputs are opposite to each other, then you'll get output as high. Okay, so we know that truth table. Now let's check the same, right? And you know the Boolean expression for this XOR is A B bar plus A bar B. Clear? So now we'll realize this into the ladder logic. So A, I can say normally open dot with B bar. So B bar means you need to use normally closed instructions. So normally closed instruction, right? Now you can give a label as A and B only. Don't put the bar, right? So it would be B, but in its complement form. Got it? Now plus operation means parallel for A bar. So normally closed in series with B. B normally open. Clear? So again, this is A and this is B. A in its complement form. Remember that. Followed by output. Understood? Now let's verify the logic. 0 0 A0 B0 with no change at all. So here A remains open, so no continuity from here, and here in the B it's open, no continuity from the branch. So from both the sides no continuity, so it means the output remains 0 only. True. Next 0 1 0 1. So A is unchanged. A is unchanged because A is 0, so it remains open. It means no continuity from this side, whereas here A is 0 and here it is closed, and B, here the B is receiving as input 1, so it means here this B becomes open because this closed instruction becomes open, and here the open instruction becomes closed. So here it is closed, the continuity will come from the branch. Okay, so it means the output will be high. Clear? Now next case, that is 1 0. Now this time A is received input but not the B, so it means this normally open instruction becomes closed, and here this closed instruction becomes open. So it means this is closed, the continuity will come from this side. Understood? But not from the branch. It means the Q is again on. Got it? Now finally, when A and B, when both are high, it means again this contact becomes closed and this contact becomes open. This contact becomes open and this contact becomes closed. So still there is no continuity from both the sides, so still output remains 0. Understood? So this is how we can develop the ladder logic for any given Boolean expression, right? So you can able to develop any kind of a combinational design with the, if you remember, simple things, right? So we'll continue more on the next lecture. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.